With physical optics, we explored the concept that light can be considered to act both like a wave and a particle. But in this laboratory experiment, we will explore a special circumstance, where light in the form of a wave appears to be directly converted to particle emissions. Within the photoelectric assembly are two charged metal plates with some known potential difference between them. As early as the 20th century, it was discovered that if incident light is exposed to these types of charged plates, that electrons are able to escape the surface of the photoelectric plate, creating a measurable current flow toward the collector plate. It was also eventually determined that the energy associated with each discrete packet of light energy was a function of its frequency and Planck's constant. Therefore, a photoelectric assembly may be used to experimentally determine Planck's constant if the frequency of light applied to the system is known, as well as an experimental stopping voltage for the electrons ejected by the photoelectric plate. We will begin this laboratory experiment by mounting both the mercury light source and the photodiode enclosure to the metal track. Each enclosure has a set screw on one side and a location indicator on the other side. We will slide the enclosure such that the location indicators are precisely 35 centimeters apart. Then, utilizing the set screw, we will secure the enclosures in place. Next, we will connect the mercury light source to its power supply, and we'll go ahead and turn on the light by depressing the power button on the power supply. The mercury light takes at least 10 minutes to warm up, so you may want to make a note of the time or even start a stopwatch if you have one handy. This mercury light source is specifically used for this lab because it emits a relatively narrow frequency of light, which is important for determining the energy of the photons later. With the mercury light heating up, we'll initialize both the DC current amplifier and the tunable DC power supply by pressing their power buttons. Not unlike previous labs, these two devices serve nearly opposite purposes. The power supply will be used to apply a very specific voltage to the photoelectric assembly, while the current amplifier will work like a more precise DMM to measure the drift current between the two charged plates of the photodiode. Looking first at the DC power supply, we will only be using the right side of this device. Near the top left corner of the right side control panel is an orange button. This sets the output voltage range of the power supply. We will require the lower range, from negative 4.5 volts to 0 volts, so the orange button should not be depressed. Shifting our attention to the current amplifier, the knob on the left side of the device that selects the current range should be rotated fully clockwise to the smallest measuring range of 10 to the negative 13 amps. To calibrate the device, we will depress the orange button labeled Signal, which is located near the top middle of the control panel. Then we'll rotate the current adjust knob until the readout screen shows 0 amps. This should be completed with care to ensure good data collection later. Once the device is zeroed, make sure to press the signal button again to change the device back to the measuring mode. The signal button will not be used again in this lab because any additional modification would create inconsistencies in our data. Next, we'll locate a BNC cable and use this to connect the input signal port on the current amplifier to the port marked K on the photodiode enclosure. We'll also use the banana cables to connect the DC power supply to the photodiode assembly as well. If it has not yet been 10 minutes since the mercury light was activated, you will need to continue to wait before moving on to the next procedure where data will be collected. Once the mercury light has completely warmed up, the cap covering the aperture may be carefully removed. On the photodiode enclosure, there are a series of both different aperture sizes and wavelength filters. The indicator at the top of the rotary selector shows which aperture and filter are currently selected. To change the aperture, the rotary assembly should be gently pulled away from the photodiode enclosure, at which point it may be rotated to select the appropriate aperture. Initially, we will select the 4 mm diameter aperture. To change the wavelength filter, the outer wheel of the rotary assembly is easily rotated. Initially, we will select the 365 nanometer wavelength filter. With both the aperture and filter correctly set, the cap covering the end of the photodiode assembly may be removed. We will then turn our attention to the power supply and current amplifier. While watching the readout for the current amplifier, we will slowly increase the potential on the plates for the photodiode by rotating the voltage adjustment knob. As the potential difference, or voltage, between the plates is increased, you should observe that the current gradually falls. This is because we are making it harder for the electrons to escape the photoelectric plate. Eventually, you should find that at some potential, the current reading becomes zero. The voltage that correlates to zero current flow represents your experimental stopping potential. This value should be recorded on your data table. We can then select the next filter to repeat this process and find a new stopping potential. A total of 5 different wavelengths should be tested with the 4mm aperture. Then the 8mm aperture should be selected and the same experimental process repeated.